Hello everyone. In today's video we're going to discuss t-tests and one-way analysis of variance. We're going to show demos using SPSS. So first we're going to load the vision data set, and we're going to look at visit 0 and age rounded 7. So here is our vision data set. And we're going to go to Data, Select, and if the conditions are satisfied, we want visit equals 0 and age rounded equals 7. Okay, so you can see here we get rid of a lot of cases, but there are still a few in there. Let's see if we can find one. So this only has people that start out. Okay, so here's a person, their visit is 0 and their age rounded is 7. So that meets our qualification. Okay, now what we want to do is compare people who at the end of the study were myopes and those that were emmetropes. We want to see how they did, 7-year-olds who came in for the first time. And we want to compare their spherical equivalents between those two groups, myopes and emmetropes, and we want to also look at peripheral refraction. So let's go to Analyze, Compare Means, t-tests, and last refractive status is our group. Now there are 5 categories there. We want category, actually let's see if we have that labeled. Cancel. Let's look at variable view, last refractive status. Let's come over here. And 0 is extreme myope, 1 is myope, 2 is emmetrope. So we want to compare groups 1 and 2. So define groups 1 and 2. And then we want to look at spherical equivalence and relative refraction, peripheral refraction. Notice that here we have init years and years. If we sit on this, we'll see that relative peripheral refraction is also, it also shows up on the right. It's in parentheses at the left. One of the problems with, I think, with limitations with SPSS is it shows the label and not the variable name, and you need to figure out what that is. So what I do when I put in, like this is last refractive status, I put in the label for that variable last refractive status and then tell what it is in the label. That way I can easily find what I'm looking for over here. All right, so we want that, and we want spherical equivalence and relative peripheral refraction. For options, we're going to exclude cases analysis by analysis. In other words, if there's a spherical equivalent missing but not a peripheral refraction, it will include that case in the peripheral refraction but not spherical. Exclude cases listwise only includes the variables that you're looking at. So if we were missing lens diameter or something about the lens, it wouldn't eliminate the case, the subject. All right. Bootstrap is another way of doing the t-test that we're not really going to talk about today, but we'll get to that later. It's just a way of randomly sampling when you don't believe you have a good estimate, a way to estimate the standard error. It's pretty useful technique. All right, so we put this out here. So we want to compare it. And one of the things, so let's go to Excel and let's copy our statistics over here. And let's copy our results of the independent t-tests down here. And notice we have spherical equivalence and peripheral refraction. Now we want to do the effect size. So there's a couple of ways we can do it. We can use the mean difference in our results here and then multiply the standard error times the square root of n, but that actually is probably not the standard way of doing it. Instead, we're going to come up here, we're going to say equals myope, and we're going to use emmetrope kind of as the base. So it's myope minus emmetrope divided by the average standard deviation. And what did it not like about that? Oh, oops. Let's do the mean. Not the name. Probably work better. Okay, so we have a minus 1.4. So our myopes have about a standard deviation, a little over a standard deviation, less spherical equivalence than the emmetropes. We can copy this formula and paste it down here. Now, we're near trivial difference with respect to relative peripheral refraction. Let's come over and take a look at, let's go back to the output. It's the same thing in either one, but here we can look at the output. So we have Levine's test for equality of variances. Remember, the t-test assumes independence, it assumes underlying normality, and it assumes equal variance. And here we do an F of the larger variance, which would be the emmetropes divided by the myopes, but it's variance, so it's these numbers squared, gives us 0.165. The significance is 0.68, so we have met the assumption of equal variance. So we take this top line, there are two lines, equal variance assumed, equal variance not assumed. We take the top line when going across, gives us the t-value, which is highly significant, the mean difference, standard error of the difference, and the upper and lower confidence intervals of that difference. So if you were reporting this out, you could report the difference and the confidence intervals of that difference. For peripheral refraction, the ratio, these variances here, the myopes have larger than the emmetropes. The ratio is 1.9. That's still not significant, in 0.15. And you can see the t-test is a little bit lower for the equal variance is not assumed. But we can still use that one because this difference is not significant. The degrees of freedom are in the two sample sizes, so 102, well, I guess it's 102 plus 418, that's 520, minus 2. so it's 518. The p-value is a lot smaller down here, but let's recall that, okay, that's significant at 0.02, but the effect size is really pretty trivial at 0.2478. So there's not a big difference in relative peripheral refraction between myopes and emmetropes at the first visit when neither group is, so the myopes, that's their final status, they're not myopic on the first visit. So that's kind of interesting. The other thing that I think is interesting is note they're both in myopic defocus. So my question is, how do myopes become myopic if their peripheral refraction is in myopic defocus, when the whole idea of treatment and progression of myopia tries to make people myopic defocus? These guys are going to progress to myopia even though they're already there. So, a question to ponder. All right, so that's effect size. We've looked at the different things, and one of the questions we would have, are these two groups, myopes and emmetropes, are they significantly different? Is this mean significantly different from 0? Does this mean significantly different from 0? These are negative. Are they significantly different from 0? So let's go in again and look at analyze, compare means. But this time we're going to do a one sample t-test because we want to know individually if the myopes or emmetropes are different. And so we come down to spherical equivalent, relative peripheral refraction, and our test value is 0. Now we can make this like minus 0.5. We could make it any number we wanted. Right now we're going to test it at 0. The options, it gives us confidence intervals, a range we could do for that, exclude, analysis, and so forth. And then again we can do the bootstrap. Okay. So let's look what we have here. Notice that for both spherical equivalence and relative peripheral refraction, both are significantly less than 0, or different from 0. In the case of spherical equivalent, it's greater. In the case of relative peripheral refraction, it's less. Now, one thing that we have to realize here is this is everybody. So really we should data split and do it for each of our groups. We'll do age rounded. Let's do last refractive status. And let's run it again, compare means. Okay. Now we find for each one, extreme myope to extreme hyperope, are they different? And we look down here and we see that for extreme myopes, they are different for spherical equivalent, but not so much for relative peripheral refraction. But we're asking about myopes and emmetropes. They are both different. So here, we come up here, we see that myopes have a mean of 0.28 and a peripheral refraction of minus 0.33. Emmetropes are 0.96 with a peripheral refraction of minus 0.5. We see both of those are different, very different from 0. Again, we get our data, our t, the difference, and the confidence interval. All right, so what else do we want to do? We had to, in order to find these separate means, we can only do a t-test 2 at a time. Now you'll see papers where they go through for the independent t-tests and they do all possible pairs. That's really quite awkward. It would be nice to not have to do that. And the way you can do it without doing that is a one-way analysis of variance. So let's look at all our things. First of all, we have to remove our split. Data split. And we're going to leave that there, but we're going to just analyze all cases, so that gets grayed out. Let's go analyze, compare means, one-way Anova. We have those two, and we have our factor, last refractive status. We can look what are contrasts. If we were going to, for example, look at the linear relationship between these 5 groups, we could put in polynomial and we could determine if this is a linear relationship here, or a quadratic, or whatever. We're not going to do that at this point. Post hoc tests. These are all the multiple comparison types of tests that can be done. Our principle, our main, at least my suggestion, is a protected least square, or a protected least squares difference. That is, we will only consider post hoc tests if the overall probability, the overall F statistic was significant. Then we can look at least significant differences to determine which pairs are different. The least significant differences do not adjust for multiple comparisons. So it's the same 0.05. That does threaten alpha a little bit, but if you adjust, say doing the Bonferroni, which is probably the next best thing to do, well, it kind of depends. Actually, Reg-Wef is probably the fairest way. Bonferroni is a little conservative. This isn't quite as conservative. But the LSD does not threaten the power. So we kind of look at the overall alpha from the F test to kind of protect our alpha level, and then we use the LSD test to protect the power. But you're between a rock and a hard place when you do multiple comparisons, because you are letting chance creep in there. Okay, what else do we have? Options. We want our descriptive statistics, gives us our means and standard deviation. We want to test for homogeneity of variance, and we'll exclude cases by analysis. And again, we can do a bootstrap. All right, so here we have in our descriptives, we have spherical equivalence for all 5 groups at once, and we have refractive peripheral refraction, the means of all 5 groups. We look and we say, uh-oh, we're not exactly equivalent on our homogeneity of variance. And if we look at our standard deviations up here, we can see our extreme hyperopes are really messing us up. They're going to increase the mean square error, this value right here, which is the denominator of the F ratio. So this F ratio is the mean square between groups divided by the within. And this number is a little higher because of the increased variance of the extreme hyperopes. So it's still way significant, so we're going to be okay with that. And then here are LSD, least significant difference, multiple comparisons. And the way this works is extreme myope compared to everybody, myopes compared to everybody, emmetropes compared to everybody, hyperopes compared to everybody, and so forth. You'll find that when we look at myope versus emmetrope here, the difference is minus with the standard, and the p is 0.000. If we were to calculate the effect size based on this, well, we'll do that in a second here, but you'll see that it's a little different from doing it the way we did it before with the t-test. All right, so that is our differences. You'll note also we have, for example, myope versus emmetrope, and we have emmetrope versus myope, and that's 0.21305, the difference 0.21305. So this table has twice as many paired comparisons as it needs, because basically it duplicates those comparisons. So there's really only half as many multiple comparisons as it appears. All right, let's look at our means. We want to compute the effect size. Copy. Let's guess we can put that right there. And let's go down and let's put in our Anova table. Copy. Let's put that in right there. Now, when you do a least squared significance test, the estimate for the standard deviation is one of the, well, we can do the effect size based on based on the same test that was with our least significant test, and that uses the mean square error term. The mean square error term is the within group variance. So since that's the variance, the variance is equal to the standard deviation squared. So if we take the square root of that, we get the estimate of the standard deviation. So let us take our, come over here, we're going to say equals the mean of the myope minus the mean of the emmetrope divided by the square root of the mean square error. Okay, I don't know why you didn't like that. Oh, because I have a thing there. Square root of this value and we're minus 1.09. Now let's do the same thing with relative peripheral refraction. And let's put this guy up here. And so 2.4. So notice this is minus 1.094. And before we had minus 1.14. So what's the difference? And let's look at our means here. 28, 62, and 58. 28, 62, and 58. So this difference is because we're using the pooled standard error. And remember, the hyperopes are increasing and making this standard deviation, this variance, greater than it should be. Our assumption is they're all equal, and by including this group, we're kind of making it the standard deviation bigger, thus making the effect size a little smaller. Okay. So I'd like for you to think about looking at this analysis, and then what does what do these data tell you about the growth of the eye, just at visit 0 and age 7, and the prospects of developing into future hemetropes or myopes. All right, something to think about. All right, next, let's look at paired t-tests. Now, I don't have any paired data in this, so what we're going to do is we're going to load the chow data. And that looks like this, and the paired stuff we have relates to axial length. So we measured axial length at baseline and then year 1, 2, 3, 4, 5. So let's look at axial length at 0 compared to axial length at 5. Now in the Chow data set, this is an ortho case study, and we had two different lens types. We had spherical and aspherical. So let's go split the data, because we don't want to combine and look at this pre-post across both types of lens types. So we'll look at lens type and okay, and then let's do analyze, compare means, paired samples. We're going to put in 5 and 0. And what are our options? We can look at this confidence interval is 95. We could make that 84 if we wanted to do some confidence limits later, but that really doesn't apply in this case. We want to maintain 95% because it's the paired t-test tests against a difference of 0. It's essentially the same thing as a one-sample t-test of the differences. The differences should equal 0. That's the null hypothesis. In this case, though, we have two columns, so we do a paired test instead of a one-sample test. There's our bootstrap we could do. All right. So what we have is the spherical lens. The axial length is 25, the mean, and the baseline was 24. So for spherical, we can look down here and see that they differed. So the spherical lens axial length grew by 1.3 millimeters. The aspherical lens was 24.96 versus 24.56. They grew 0.4. Here's the T. They were both highly significant. So both lenses grew over time in these kids. But if we were to do an independent test, t-test between spherical and aspheric, we would see that the spherical grew a lot more than the aspheric. Another thing you got to watch out for is it gives the paired samples correlation. So pre and post in the spherical were correlated with an R equals 0.63, which was significantly different from 0. And so did the aspheric. Remember, they didn't grow as much, so they're a lot more correlated at their second visit, or their 5 years later, because they didn't change that much. But they're both correlated. Don't confuse this with the t-test. The t-test p-value is down in this next box. All right. So that's all I want to talk about today.